Okay, hello everyone. So in today's meeting, we're gonna, talk about integration on manifolds. But in order to talk about integration on manifolds, we first need to talk about a couple things. So one of those things is orientation. So when we integrate an Rn, we took, the um, measure theory route, and we define integration by looking at by looking at some sigma algebra. We took the Borel sigma algebra and then extended it to the Lebesgue um, algebra. And the way we defined integration was then, just measurable functions, and then you take volumes of measurable functions by, the measure, and then, adding them all up together with the Lebesgue integral. So in that construction, we never explicitly made use of an orientation, right? Because it didn't matter like how everything was oriented. And so this suggests that there is a method of defining integration on manifolds that does not require an orientation to begin. So why do we care about orientation? So, so why do we care about orientation? So one of the main reasons is when we swap order of integration, for example, so if we had integral of a, b, f, we would want this to equal the integral from b to a, negative the integral from b to a of f. And this sort of construction uses the fact that we've, oriented the line. So we have oriented AB so that A to B is positive and B to A is negative. Now, we would have never gotten this sort of orientation with just the simple Lebesgue measure. And so, in order to keep, bounds of integration things and other things from vector calculus intact, we do need to talk about orientations. Okay, so what is an orientation? So before we even jump into the, general case with manifolds, what we're going to do is we're going to start with vector spaces. Um, because R is a vector space, right? Rn is a vector space. So let's see if we can use vector spaces um, to, get an intuition for what orientation should be. And once we define that, we can then define orientations on manifolds, since we have a collection of, like, canonical collection of vector spaces associated to a manifold through the tangent bundle. So okay, so in I think the most natural place to start, in fact, is R3. In R3, we have basis vectors x hat, y hat, z hat. And in some sense, we say that it's positive, like this is like in some sense it's like left-handed orientation. Oh, sorry, yeah, it's sort of like a left-handed orientation, but I don't really like that naming because it's very hard to sort of visualize which way is what. So we're gonna say that okay, in some sense this is positively oriented. Okay. And then we use the cross product to give us the rest of the orientation. So for example, um, sorry, let me rephrase that. So these three basis vectors define an orientation, right? They say that going from x to y is positive, but going from y to x is negative. Similarly, going from z to x is positive, but going from x to z is negative, right? So we want to somehow, you know, make this more precise. Um, and so before we even get there, note that, the cross product already gives us um, a way of checking if this is aligned with our orientation or if it goes against our orientation. So if I took x hat cross y hat, I would get z hat. But if I took y hat cross z x hat, I would get negative z hat. Right? So this sort of suggests that XYZ is positively oriented in some sense, and Y X negative Z are also positively oriented. So let's make this more precise. Um, if V is a vector space, again, remember we're just working with finite dimensional real or complex vector spaces. In this case, we're gonna deal with real vector spaces. Um, vector space with two bases. Um, actually, even before we even get there, um, so now we have the map. Like we have a map from R3. We have a linear map from R3 to R3, given by x hat goes to y hat, y hat goes to x hat, and z hat goes to negative z hat. In a matrix, this has the form, um, let's see, one like this, and then one like this, and like this. So how do we check, like, what object could we check on this to, give us of whether this should be positive or negatively oriented? And the most natural thing that comes to mind is taking the determinant, because the determinant sort of tells us, are we flipping the areas of things, of the parallelogram spanned by these things? So we should take the determinant. So taking the determinant, um, we get, okay, so the only non-zero entry is, from this one, and that has a minus sign associated to it, determinant of 1, 0, 0, minus 1, and this is 1. So this tells us, okay, that these two bases are positively oriented with respect to each other, right? They're in the same orientation. Um, Similarly, if I simply mapped x to y hat to x hat, and z to z hat, right? Then we would see that the determinant would be -1. And since it's -1, we see that it's, it's negatively oriented with respect to the standard orientation on R3. So we can now make this more precise. So let V be a vector space, be a, real vector space, and let V1 up to Vn and W1 Wn be two bases. Then these are oriented, um, with the same orientation if the map, the linear map F, mapping Vi into Wi has positive determinant. And similarly, they have opposite orientations if the map has negative determinant. Just write this really quick. They have opposite orientations if determinant F is less than 0. Um, okay, and now I think it's pretty clear to see that this map will always either have positive determinant or negative determinant. And this just follows from the fact that we're mapping linearly independent sets into linearly independent sets. And so this map is an isomorphism. Hence, it must be invertible. But since it's invertible, it must have positive or negative determinant. It can't have zero determinant. What this now means is that if we take the collection of all bases on a vector space, you can partition them into two pieces exactly. Those um those so that when you move between them, you have positive orientation. I say you have a positive determinant, and when you move across the partition, you pick up minus sign. So let's make this more formal. So we can define an equivalence on the set of bases. And you can also think of this set of bases as the general linear group of the vector space, right? Because they just give you every linearly independent map. So set of bases, i.e. on GLV, um, so that um, um, the map actually, so we can define an equivalence on the set of bases by um, V1 up to Vn is, an ordered basis is equivalent to W1 up to Wn if a determinant of f is bigger than 0, where f is defined as above. Yeah. So I mean, all this is saying is that, when you change basis from one basis to another, um, you don't like change sign. In other words, the parallelogram remains oriented the same way. So it's very important that we actually have, an ordered basis here, because as we saw here, simply swapping the order of two elements that are, adjacent to each other, you pick up a minus sign, right, in the determinant. So, um, you do require, like, on the set of ordered bases, and like, let's do this ordered bases, and that is the general linear group. I will let you think about why that is the general linear group. Okay, so with this in mind, like, this partitions into two things, right? A positive, well, I don't want to use that, but yeah, it partitions it into two. So we therefore partition the set of bases into two pieces, right? And then a choice of equivalence class, let's say we'll denote it by these square brackets, is then called an orientation. So the idea is that instead of choosing a particular basis, you just choose an equivalence class of bases. So you can move between two bases in the same orientation. And if we have, so if actually, I don't want to make this like precise, because yeah. So basically the idea now is that if you have a vector space and you choose an orientation, we say that any basis that is equivalent to this choice of basis is said to be positively oriented. And if you take if you relate it to a basis from the other equivalence, we would say that the other basis is negatively oriented. But positive and negative orientation heavily depends on the choice of initial equivalence class. Um, so I didn't want to make that. So yeah. Um, okay, but now this is like fine, but is there a way that we can sort of define this without um, using a particular choice of bases? Because choosing bases are just kind of annoying. Um, and we want to think about what objects do we have on manifolds that we've been working with that could potentially convey the same information, and that's using differential forms, right? Because they're just alternating covectors, and we've been using the determinant. So we can define the determinant form on a on a vector space by taking the vec product of the duals of the particular choice of basis. So now given this orientation, um, we can define like an omega in as an n covector by the fact that omega just equals V1 uh, wedge with itself. Um, and now, okay, this is sort of ill-defined. Um, and to rectify this, what I'm going to do is this is ill-defined. So what I'm going to do is instead of choosing an orientation, we'll choose a particular basis. So, but if we choose a particular basis, in this orientation, then omega is well defined. Yeah. So in this case, instead of choosing like an orientation, we just pick a basis. And we don't even need to pick a basis now, because all we need to do is we need to pick um, an n form on the vector space, and then we take the orientation defined by a basis so that when we apply this n form to this basis, you get 1. So note if omega is in and omega is not 0, then we can find a basis. V1 up to Vn so that omega applied to V1, Vn gives me 1. Then we can choose this basis as our orientation. So, okay, so we've gone from, choosing a basis to choosing an equivalence class of basis to choosing a nowhere vanishing top form. Right? So that's the main idea now. So an orientation is equivalently a choice of basis, or it's a choice of nowhere vanishing top form. So an orientation on V is a choice of omega in this set. Okay. And now this leads like naturally into the definition of an orientation on a manifold, right? Because we can replace this space by, the space of n forms, and then we can replace this one by the zero section of the n forms. So what this is saying is an orientation now an orientation on a manifold is a choice of omega with omega p not equal to 0 for all p. You know. Okay, so in the case of vector spaces, this choice, we could make this choice of top form, right? We could always, just pick an arbitrary basis. It doesn't matter which one. Um, and then we could take its associated volume form, and that would give us an orientation on the vector space. But now the question is, okay, does such a orientation always exist on an arbitrary manifold, right? So does such omega dep- uh, does such omega exist on all manifolds? And the answer is no. And the reason the answer is no is, well, for one, we'll see that, an orientation is equivalent to the choice of choosing a direction that points up, whatever up means. Um, and not only that, actually, it is that. And therefore, if you look at the Mobius band, for example, um, so if you look at the Mobius band, for example, you cannot choose such upward pointing vector at every point in a continuous way, right? Um, there is no way to choose an upward pointing vector field on the Mobius band in a continuous way. And this is because if we, go around the Mobius band once, what was pointing upwards is now pointing downwards. Um, so there's no way to do this in a, continuous way. I will leave it as an exercise in like one of the problem sheets, um, where given like I will outline the proof that an orientation is equivalent to this choosing of like upward pointing normal vector. Sorry, upward pointing vector field. Okay. So now nowhere vanishing top form is a very long name, so I would say that such a form is called a volume form. Such a form is called a volume form. Moreover, if such omega exists, we say M is orientable. Yep. And we'll see that there are a lot of like non-orientable manifolds that we do care about. So for example, the Mobius band is an example of a vector bundle over the circle, right? You can think of a Mobius band as a vector bundle. Um, and therefore, it's non-orientable. Um, so we will develop the theory of integration uh, for orientable manifolds. But equivalently, there is a theory of integration for non-orientable manifolds. Um, I don't think I want to spend time on that, but I will um, give an exercise or two about like the bundle of densities, um, which is used in defining the integral of non-orientable manifolds. Well, integral over non-orientable manifolds, I suppose. Um, okay, so yeah, what did I want to say? Okay. There's also another way of looking at orientability, and but we'll look at what like that way is once we talk about principal G bundles. So we'll talk about like orientability in like a much, I guess, stronger way once we talk about like principal bundles. And I plan on talking about principal bundles after Riemannian manifolds, or at least around when we talk about Riemannian manifolds, because I think a lot of ideas from Riemannian manifolds could help understand like the use cases of principal bundles. Um, okay, so even though every manifold isn't orientable, every manifold is locally orientable. So every manifold is excuse me, locally orientable. And the way we prove this, so proof, is as follows. So let U phi be a chart on M. Let omega equal, the usual volume form on Rm. And then we can restrict omega. So then we restrict omega to, phi of U. note that since phi is um, a diffeomorphism, um, d phi um, from the tangent bundle of u into the tangent bundle of phi of u is um, is invertible. Uh, Hence, pulling back by the inverse is a volume form on u. Okay. So what this says is that every chart is orientable, basically. Um, and then we can say that, okay, the orientation induced by a chart, it's called, well, a chart oriented, well, a oriented chart, I suppose. Um, okay. So that's this is one very useful result. Another thing is note that this means that if um, f from m into n is locally is a local diffeomorphism, and omega is a top form on n, then at the pullback of omega is a top form on m. So I mean, this now shows that, okay, the Mobius band isn't locally diffeomorphic to like any sphere, for example. Um, so I mean, you can check that any sphere is um, orientable. But once we talk about Riemannian geometry, I will outline a much more clear proof, or one much more direct proof that every sphere is orientable. Um, okay. One final thing I want to say is that F is orientation, excuse me, is orientation preserving um, if df at P is an isomorphism mapping uh, actually the easier way to say this is that if the determinant of df at P is positive, and F is orientation reversing if the determinant of df at P is less than. So like these are definitions that we would expect to be true, at the very least. Okay. Um, okay, so that's all I really wanted to talk about in terms of orientations, right? The main idea is that an orientation is simply the choice of a top form, or like a volume form. Not every manifold has such a volume form. Um, and yeah, I mean, that's about it really for orientations at least. Um, Now I want to talk about. Okay, so I know this might be jumping around a little bit, but I think the most natural thing to now talk about would be manifolds with boundary. Because so far we've looked at the circle, right? And spheres, for example, they're manifolds. And the closed ball, sorry, the open ball is also um a manifold. But you would expect that the closed ball also be a manifold, right? Because at each point, it sort of looks like some sort of space that we're like, you know, reasonably comfortable with. So why not add, these like half open spaces, well, I guess it's not half open, it's like half closed spaces to also be part of our manifolds, right? So, and this is what a manifold with boundary is. So we're going to define um, Hn to be a subset of Rn, and it's going to be given by um, the condition that Xn must be bigger than or equal to 0. Okay, so it's not just the upper half plane, but it's also the upper half plane, including the Xn equals 0 plane. Then M is a manifold with the boundary if for all P and M there exists P subset of M open and homeomorphism phi from U into U hat, which is a subset of Rn or Hn. And and M is second countable in Hausdorff. Okay. So it's just basically a manifold, but instead of, being locally homeomorphic to Rn or like an open subset of Rn, it's locally homeomorphic to an open subset of either Rn or Hn. Um, okay, I mean that's pretty okay. Now um if phi of U intersect Hn is empty, right? Then this subset is actually just a subset of R, like just an open subset of Rn. So then we say P is an interior point. Because it's not really a boundary point, right? Because we never had to use the fact that, it intersects or it looks like the upper half plane at any point. But if the intersection is non-empty, then we say P is a boundary point. So in this case, we are using the fact that, okay, now this open subset of M actually sort of looks like it has a boundary. Right? The other one didn't really look like it has a boundary because we can like approach points on the boundary, but the boundary is outside of it in some sense. Right? And so yeah, we denote we I mean we call the boundary of the manifold just the collection of boundary points. And we note that this is also a manifold. The boundary of M. And in this case, you got to remember that this is not the topological boundary of M, but is rather the manifold boundary of M. Um, yeah, we call this a boundary. And an exercise, all right, an exercise is to show this is a manifold, is a dim M minus one manifold, smooth manifold. Okay, wait, I just realized I really forgot to define a chart. Let's let's do that really quick. So we define, compatibility in the same way. So we define smooth compatibility, 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 compatibility to be, um, phi composed psi inverse, is extendable. Um, so we have to be able to extend it to extendable to a smooth function on an open set in Rn. So if these, oh, I've not been using like half the board. So if you have a manifold with boundary, um, and it turns out that okay, you're looking at charts on the boundary, they're gonna overlap on some uh, open set in HN, but open sets in HN could have like this boundary that we've defined. And the way we defined smoothness of functions was on open sets. So the way you define smoothness on these like um weirder sets is you say that okay, if you can extend it into some open set containing this new set, and the function is then differentiable at all the points in the space, then you say that your function is smooth. um and this allows us to now define C infinity compatible charts, and hence we can define a smooth atlas. Analogously define a smooth atlas. Okay. Now with this smooth atlas, M is called a smooth manifold with boundary, but as usual, we'll just omit the word smooth and then we'll just worry about manifolds with boundary. So yeah, then we can talk about the boundary of the manifold, which is just the collection of all the boundary points of the manifold, and this is now an dim M minus one dimensional manifold, without boundary. Okay. Um, I mean, we also have the interior of M, which is just P and M such that P interior point, is also a manifold. So exercise, show interior M is a smooth manifold. And like what is its dimension? It should be pretty obvious what its dimension is. I'll let you guys think about how to take charts on the interior of M. With the boundary of M, you still have to think a little bit about um, how to get proper charts that don't map into HN, but that map into RN, um, RN minus one, I suppose. But with the interior, I think it's pretty clear like what it is. Um, it is a non-trivial fact, in fact, actually, that the interior of M and the boundary of M are disjoint. But I feel like once prove this stuff, it should become pretty clear that uh they can't intersect at any point, because then by the um I forgot what I called the theorem, but invariance of domain, I think. You would get some like things that clash. So yeah. Okay, so we now have an operation on the category of smooth manifolds with boundary. Oh yeah, also like smooth functions defined analogously, like uh you take the um you take the coordinate representation of the function, and then you say that, okay, I should be able to extend this to some function on some open set in Rn, and then you talk about smoothness. Similarly, and then you can define the category of smooth manifolds with boundary. Um, okay, so let's just define that really quick. So let M and N be manifolds with boundary. Let F be a smooth function from N to M. Sorry, let F be a map from M to N. Then F is smooth if for all P and M there are charts um, U phi in M containing P and chart and V psi in N containing F of P such that the map phi inverse composed F composed psi is a map is smooth. You know, in the usual sense, right? Like this is now smoothness of functions defined in the real space. Um, and then these could be defined on some open set relative to the upper half plane. But then we know how to define smooth functions there. We just, again, we say that we can extend it to some open set containing this other open set. Um, so yeah, we can then define the category of smooth manifolds, right? So we then have um, the category of smooth manifolds with boundary. One interesting thing to note is that um, an interesting thing to note is that we now have a map from the space of smooth manifolds with boundary into the space of smooth manifolds without boundary, right? So we have a map that I'll call del, right? It takes smooth manifolds with boundary into smooth manifolds, right? In such a way that taking the boundary of M is, empty. This is because we proved here that the boundary of the manifold is a manifold without boundaries. So the boundary of the boundary is empty. And in some sense, there's sort of a duality going on here, right? Because we we have a map D, right, that takes n forms on M into n plus one forms on M with D composed with D equal to zero, right? Or in other words, D of D omega was zero. So now, but in this case, instead of going up a dimension, we're coming down a dimension. So the boundary, um, maps you down a dimension. And this is sort of the idea with homology. So if you remember, we defined the cohomology, the deRham cohomology of a space by looking at, the exact sequence um, given by the exterior derivative, and then we took like some quotient vector spaces. Um, and we call that the cohomology. And we similarly have a very similar object with manifolds with boundary. And this is related to the idea of homology. This is not quite this is not quite what homology is, but there might be some sort of way to define homology with this. I'm not sure. Um, but yeah, if there is a way, just let me know if you guys find a way. But yeah, I this is just an interesting duality that I sort of saw. And then you can ask similar questions. Is every manifold the boundary of some other manifold? Right? Um, and that's also an interesting question to ask. So, you know, given this, is every manifold the boundary? And this is every manifold, let's say manifold without boundary, the boundary of some manifold. Um, and I mean, the answer is yes. Um, so I guess the more interesting question is, so yes. Um, So, I mean, just consider, um, for example, just consider this manifold. Right? This is a manifold with boundary. This is a manifold, and then the boundary of this manifold is just M, or at least it's diffeomorphic to M. Um, so yeah. Okay. So and now exercise is actually no. I mean the other one. The other question is like even easier to answer. Is every manifold with boundary the boundary of some manifold? And the answer is no. Because if it was a manifold, if it was the boundary of some manifold, then you found a manifold whose boundary has boundary, and that contradicts um this thing that we said over here about the boundary of a manifold. um so okay, in this case, like the duality is not. I don't know, again, I don't know if it's enlightening or not, but this is just something interesting that I've noticed. um okay, let's now quickly talk about the tangent space for manifolds with boundary. And everything we need to know about the tangent space of a manifold with boundary is just given by the tangent space of the upper half plane. So exercise, show, sorry, um, sorry, 1 second. I think I've forgotten to define what the tangent space of the upper half plane is. So let's talk about that really quickly. Okay, so I mean, so let P be in Hn, then um and I from Hn into Rn be the inclusion map. Then dip from the tangent space into the tangent space of Rn is an isomorphism. And so basically what we can say is that the tangent space of the upper half plane is just given by Rn. Okay. Um, with this out of the way, it's now an exercise, I suppose. Um, Actually, it's not really an exercise. Then we can define the tangent space at the boundary of the manifold um, by using this. So we can then define TPM for E in boundary of M um, by taking a chart and then saying that it's just this tangent space. And this is sort of similar to by taking chart, by taking a chart and using that to define TPM. Similar to how we did with manifolds without boundary. We used charts to induce isomorphisms, and then we said, okay, tangent spaces are basically just Rn, and then you define coordinates on this, we can use the derivative. um okay, but one thing to note um is that TP boundary M is not the same thing as TPM, right? And this is because this is n minus one dimensional, so this is m minus one dimensional, and this is m dimensional, right? So I mean they can't be equal. And then with this we can say that XP in TPM is said to be tangent to boundary of M if XP is, in the tangent space with the boundary, which is a pretty obvious definition. Um, and then now one thing to note is that, okay, for example, let's say we have the upper half plane like this, right? This is the upper half plane. Now, if we have a velocity vector coming this way, its tangent vector sort of points outside the upper half plane. So its tangent vector sort of points outside the upper half plane. Um, this then gives us motivation to define something known as an outward pointing tangent vector, right? Just to be a thing that starts at some point and then at zero it comes in, it starts on, let's say, the interior of the manifold. It has to be on the interior because otherwise it's tangent to the boundary, and then this it wouldn't really make much sense to say if it's inside point, like inward pointing or outward pointing. So we start with a curve that, starts at the interior and then it comes in and then hits the boundary and then the velocity vector points outward. So we say XP, sorry, is outward pointing if there exists gamma that starts somewhere else, um, with this equal and gamma at gamma prime at zero is equal to XP. And similarly, we can start um, on the boundary and then shoot outward. So then the velocity vector would point upward and hence would point inward. So we say XP is inward pointing if there exists gamma that now starts at zero uh, with, this. Okay. So that's just the basic terminology and, the basic stuff of what we would need for manifolds with boundary. Because the main idea for today, as I mentioned before, was that we want to talk about Stokes's theorem. And Stokes's theorem, relates the integral of a differential form with an integral on the boundary of some differential form. So we would need to know what, the boundary of a manifold, sorry, excuse me, what the boundary of a manifold even is. Um, okay. One thing to note now is with Stokes' theorem in mind, we want to find a way to relate an orientation defined on the manifold with some orientation defined on the boundary of a manifold. So how do we do that? So we're going to use the following fact. So fact, um, there exists an outward pointing vector field, um, you know, on the boundary for any manifold with boundary. There exists n, which is a vector field, such that NP is outward pointing. And now an exercise, show um, show that if I take the inclusion map and I pull back the orientation form or the volume form omega. Um, so okay, firstly, I want to show this. Um, and if omega is a volume form, then so is this pullback. And this will be, an orientation. And hence, we have defined an orientation induced by M on the boundary. Hence, we have defined, hence we have hence we have an orientation on this um, given by M. Okay. So we've now taken, orientations on manifolds with boundary, and then we've restricted those orientations to orientations on the boundary of the manifold. Um, and now, one might ask, okay, if I have two manifolds, can I produce a new manifold? Like if I have two orientable manifolds, um, can I produce a new orientable manifold? Um, can I just produce a new orientable manifold using these two manifolds? And the idea is yes. Sorry, the answer is yes. So let's actually take another thing. So let M and N be manifolds. And usually when I say manifolds and I don't specify if they have boundary, I will say I will note that these are manifolds without boundary. Uh, be manifolds. Let's say they're or be orientable manifolds. Um, with forms with the volume form omega n, sorry, forms of omega m and omega n, then the pullback by the projection on M wedge with the pullback by this is a volume form on M cross M. And proof is exercise. With a lot of these exercise, I had to try it the first time. Exercise. Sorry. Yeah, with a lot of these proofs, I mean, like this one is very straightforward again. All you have to really show is that this thing is nowhere vanishing. Um, and I feel like that sort of follows. One thing you could do is you could take like charts on M and then take like the induced chart on the on the product and then like find, the coordinate representation of what these should be. Um, and you should see that this would like be trivially non-zero. Um, okay. With all of this, we can now finally define integration. Okay. We are finally ready to define integration. So what we're going to do is we're going to take some form omega, right? So let omega be some form in R. Let's start with Rn, and it must be a top form, and we'll see why in a second. Let omega be a form, uh, be compactly supported. And let U be some bounded open set. Um, containing actually just some bounded open set. Um, yeah. Note that omega, since it's a top form, it equals to some function times this wedge product, right? And this is exactly why we need this to be a top form because now the like each top form is uniquely determined by the function it multiplies this basis differential form. Um, so if we had like a bunch of, if we had like an n minus one form, for example, we would have n basis vectors, and then it's not really too obvious on how we should define integration in that regard. So we're going to define, um, so then we're going to define the integral uh, of omega over u to just be the integral of over u of f of dx1, dx2, so on. Okay. And this we know how to do. Okay. So I guess it doesn't really even have to be bounded. It just has to be some open set. Yep. And this is how we define integration. It's very simple. Um, if so, I'll leave some things in like the lecture notes. So in the actually no, let's just define it. So if f from u to v is a diffeomorphism, then the integral over v of the pullback of f, sorry, pullback of omega is equal to the integral of omega over u if f is orientation preserving, and it equals negative this if f is orientation reversing. Okay? And this follows from the change of variable formula. And we sort of require this because we need that, integration be well defined on manifolds. So if we didn't define integrals in a way that, sorry, if we didn't define integrals in a way that, was consistent, i.e. we had like a change of variable type formula, it would be extremely inconvenient, um, you know, to do anything. Okay. So now, with all of this, like, how do you define the integral over an arbitrary manifold, right? Because so far we've just been talking about um, integration over manifold, sorry, integration over Rn, but we've just defined integration over Rn in like two different ways. Um, but not really, right? Because we've just used differential forms to now talk about, some function. Um, in Rn, it makes sense because like these tangent bundles are like trivial. Sorry, these vector bundles are all trivial, right? So top forms just correspond to functions, right? They just correspond to sections of, or sorry, smooth functions, real valued functions. So in the case of like Rn, like there's nothing new that we've really defined here. Um, so how do you define this in Rn? Sorry, in over some manifold. Um, and the idea is simple. So let M be a manifold. Oh yeah, and also we're taking omega to be like compactly supported, but in reality, omega doesn't have to be compactly supported. Um, it's just that compact support allows, like less worries about convergence of integrals and stuff like that. So it's just a lesser pain to think about, um, compactly supported differential forms, but you don't actually need compactly supported differential forms. Yeah, so let M be a manifold, um, and let um, U phi be a chart. let omega be a top form in M. Then the integral over u of omega is simply the integral over phi of u of the pullback by the inverse of omega. Okay. Um, and this is like a logical definition because we've seen that, it is invariant under a change of variable, basically. So if you have this and you have like an orientation preserving change of variables, then your integral does not change sign. So this is a well-defined um, integral if you restrict yourself, even if you don't restrict yourself to like orientation preserving um, diffeomorphisms or orientation preserving um, charts. Sorry. Okay. But I mean, most of the time we will be restricting ourselves to orientation preserving charts because that's just, a nicer way to do things. But now let U alpha phi alpha be a chart, sorry, be an atlas, and let psi alpha be a part like a smooth partition of unity. Subordinate to U alpha, then we define the integral over M of omega to simply be the sum over alpha of the integral over U alpha of the pullback, sorry, of psi alpha omega. Right? And there we have it. This is how you integrate a differential form over a manifold. You just take an atlas. So you take the differential form, you take an atlas, you take a partition of unity subordinate to this atlas, and then you just integrate um, this product of the partition of unity with this form on this chart, and then you add all of them up together because you know that at each point, apart like the partition of unities add up to one, right? So you sort of recover what the original integral should be. And now I haven't really shown that, this definition is well defined because I haven't shown that this does not depend on the choice of atlas. I haven't shown that this doesn't depend on the choice of partition of unity, but this is a standard proof from analysis. So I will leave this as an exercise. Exercise. Um, read the proof of well-definedness. Right? But yeah, I mean, integration on manifolds in this regard is not too complicated, at least theoretically, because a lot of the times we don't really care about the choice of partition of unity. But in practice, this might be really, really bad, right? Like we don't really know. We firstly don't even know how to find partition of unities in general. So requiring um, requiring this definition to, use partition of unity, it seems almost counterproductive because it is very hard to, actually work with this. So the idea is we're going to take ideas from like, integration, and we're going to basically say that, okay, if you know the function in some measure zero set, um, and so you can just integrate, like you can, instead of trying to find partitions of unity, you can find like open sets that cover your space. Um, so you can find open sets that cover your space, but then they leave out sets of measure zero, right? So for example, if you wanted to integrate over a circle, you could integrate over the entire circle other than a point, right? And that point wouldn't really change the value of the integral because the things we're integrating are smooth, right? And even if they weren't smooth, right? We've seen from measure theory that two functions have the same integral uh, if they differ, like if they differ up to a set of measure zero, right? So in reality, all you really have to do is find an open cover that removes at most a measure zero set and then just integrate over that. So let's see an example of this in action. Example. Um, let M be T1, sorry, T2, which is S1 cross S1, and omega equals XYZ dW wedge dy, where uh, R4 is given by WXYZ, sorry, T2 is given by WXYZ width such that W squared plus X squared equals 1 equals Y squared plus Z squared. Um, and now you want to compute with orientation given by S1. Right. So the orientation on S1 is just, the one that goes counterclockwise around the circle. And so we have a chart. Rather, we have a parameterization of S1. We have a positively oriented parameterization of S1 given by phi from, the into S1 by taking theta and mapping it to cosine theta sine theta. Right? And now the thing is, again, this doesn't really cover S1. This almost covers S1, but we're only missing a point. And since we're only missing a point, this is a set of measure zero, so it does not matter. Right? So this means that we have a positive orientation, sorry, positively oriented parameterization of T2 given by I'll just call it the same thing phi, and it takes in, 2 points, theta and phi, and maps you into cosine theta, sine theta, cosine phi, sine. Oh my God, this is a bit inconvenient. Sine phi. And then, this will be a positively oriented parameterization of the torus because, we take in the positively oriented parameterizations of S1, and then we used sort of this construction basically um, to give us a parameterization of the torus. So now what we have to do is to integrate, so the integral over T2 of omega is simply going to be the integral over 0 to 2 pi squared of, since there's a parameterization, instead of, going from the manifold into an open set of Rn, we're going from an open set of Rn into the manifold. So all we have to do is pull back instead of taking the inverse and then pulling back, pull back of omega. But what is the pullback of omega? So what is phi of omega? And I mean, you can check really easily that the pullback of omega basically just puts in um, the x coordinate in here, y coordinate in here, z coordinate in here, and then takes the derivative of the w coordinate and the derivative of the y coordinate. So what you end up with is nothing but sine theta cos phi sine phi d of cosine theta wedge d of sine theta. Say, sorry, cosine phi. And then this comes out to sine squared theta sine squared phi cos phi d theta wedge d phi. And what this tells you is that this integral is nothing but the integral from 0 to 2 pi, the integral from 0 to 2 pi. I mean, I can use Fubini's theorem because everything converges, because everything is like compactly supported and whatnot. Um, well, it's not really compactly supported, but these functions are integrable, so it's fine. Um, of sine squared theta, sine squared phi, cosine phi, d phi t theta. And now this is regular old integration in two variables, which is zero. You can check that this integral is just zero. So okay, when it comes to, integrating over manifolds, again, it is not that bad because all we really need is um, local parameterizations of the manifold that you can all leave. You want them to be disjoint because if they're not disjoint, then you're gonna have to find like partitions of unity to, get rid of the overlap and whatnot. Um, so you can, and then you can just like avoid sets of measure zero. So again, in this case, this leaves out like it leaves out like an entire circle, right? But that doesn't matter too much because in the torus, this is measure zero. So we don't need to worry about that. So in the problem sheet, I've like, um I've given a couple I've given a couple questions where you integrate over a circle, for example. Um and yeah. Okay. So now if omega, is a top form and omega is a volume form, um, then the integral over omega cannot be zero, right? It cannot be because this function is positive everywhere, or positive everywhere, or negative everywhere. Right? It's not zero. Um, so yeah, I mean, this is just one thing to keep in mind. I'm not actually sure why I said this right now. Um, but okay, we can now finally talk about Stokes' theorem. And all it says is that if let M be a oriented smooth manifold, with boundary, with boundary, and let omega in this be compactly supported, then the integral of m over the integral of d omega over m is equal to the integral of omega over the boundary of m. And here, technically, omega is, you take the inclusion map and then you pull back the form by the inclusion map, but this sort of just corresponds to restriction of the form to the boundary. In particular, so okay, the proof of this is not actually too hard. Um, the idea is you prove it in like Rn, you prove it in Hn and Rn. Um, And once you've proven it in HN and Rn, you're basically done because, everything else follows from that. So the proof is not entirely too hard. I will outline a proof of it for the problem sheet, um, if you'd like. I might not. I don't know. If if I do outline it, you can prove it yourself. If I don't outline it, I do recommend at least trying to prove it. If not, you can check like Lee's smooth manifolds, and he has a pretty comprehensive proof about um, yeah, Stokes' theorem. But okay, why is this really good? We'll see when we talk about Riemannian geometry that this gives back the general notions of, Stokes' theorem in two dimensions. This gives us Green's theorem. This gives us divergence theorem and so on and so forth. It gives us so many different theorems this also gives you the fundamental theorem of calculus back, right? Um, all these theorems that looked disjoint from each other are actually can be written very nicely using the language of differential forms. Um, Moreover, I mean, one more thing to note is that if the boundary of M is empty, then the integral of m of d omega is equal to 0, right? So what this tells you is that if you have an exact form, uh, if you have an exact form on a manifold without boundary, then its integral, sorry, the integral of its derivative must be 0, right? Um, but okay, one major consequence of this is the following. So consequence, I guess corollary. Um, let omega, right, be a volume form. Let M be compact um, and without boundary. Compact and without boundary. Um, then omega is not equal to d eta, i.e. omega is not exact for any eta. And the proof goes very simply because okay, we know that the integral over m of omega must be non-zero, but um, the integral over m of sorry, of omega is equal to the integral over m of d eta, which is equal to the integral over the boundary, right? But the boundary is empty, so this is 0, which is a contradiction. Okay, so just having, Stokes' theorem now is starting to give us um, information about the cohomology um, of compact manifolds without boundary, right? Because now we've shown that um, the top cohomology of a compact manifold without boundary, when oriented compact manifold without boundary is empty, is non-empty. Um, and so this in and of itself is already really good. So Stokes' theorem is, a very beautiful theorem that we will be sure to keep using whenever we can. Um, but yeah, that's it for today. If you have any questions, you can ask me in the Discord, um, or anywhere, and you can ask me anywhere. And yeah, that's it for today. Thank you.